Live stream.
There it is.
Hey, welcome to the October meeting for the Baton Rouge Astronomical Society. Tonight's guest speaker should be a pretty good one. We're doing something on spectroscopy. I'm going to hand it over to Coy now for the introducing of the speaker.
All right, well, thank you everybody for coming along for the ride tonight. I know we've had a bumpy week with the hurricane coming through. I'm glad to see some faces on tonight. We have a great guest speaker tonight, Tom Field. He's president of Field Tested Systems and surprisingly a contributing editor of Sky and Telescope magazine, which we all know and love. So Tom, I'll hand it over to you and you can start your presentation. Thank you so much for coming.
Thanks, Coy, and thank you also for the work that you did behind the scenes to make this happen. Some members may not know what a ball and chain it is to come up with speakers regularly. And, you know, there's a lot of scheduling and, you know, getting a bio to the club and, you know, all those things. So thanks so much. I appreciate it. And my heart goes out to everybody, both here and down there anywhere who's been affected by the climate events that you just went through. We, of course, here in Seattle have our wildfires. It hasn't affected us directly. We had a little smoke for about a week or two. And that's behind us now, we think, for this year. So I'm going to talk for 45, 50 minutes, and then we can do Q&A afterwards. I think it'll work best that way. And let me see if I can bring up that screen. There it is. It's that little screen thing. And we'll just go like that. And then, am I sharing my screen? Can you guys see that, one of you?
Yes.
Okay, great. You mute everybody? Yeah. Okay.
Mute everybody, I
You don't
think.
have to mute me.
Hold on. Well, you can unmute. You have to unmute yourself.
Okay.
But you can mute everybody, I think. Yeah, here. I'm gonna, and now everybody's muted, and you just unmute yourself, and you can just go. There should be a little speaker icon on the bottom left next to the hang up icon. Yeah, and that should unmute you. Didn't work. Okay.
Great. You can hear me now?
Yeah.
Great.
Yep.
Okay, so let's try that screen share again. And off we go. There's that. There. Oh, isn't that pleasant? All right, let's get rid of that. Isn't that fun? And go like that. Okay, so you see that prism there, I hope. By the way, Scott, maybe or somebody, you or Coy could unmute yourselves. Do the attendees see a video window of me at all or no?
Yeah, there's a little grouping on the right side. You can scroll through it and find a picture of yourself. Yeah, you're the, well, you don't have your video playing right now, but there's a TF that represents you.
Okay, so there's no way that I can sort of hold things up to show them to the group?
I don't think you can share your screen and your image at the same time. I'm afraid.
Okay, let's just try for a second and see what. Well, there is no way to do that. I'm just thinking I could show it here. Okay, well that's unfortunate because I have some visual aids and also it's easier to stay engaged as an attendee when you can actually see the person talking. That's the only drawback I see from Zoom right now so far with this.
Yeah.
So first of all, it's
actually I've never noticed that before.
Yeah, I want to compliment, I don't know if they're here tonight, whoever created this logo. This is an absolutely gorgeous logo. I always like to put the logo up here just so, you know, it makes a little bit more of a connection at the start of a talk. And I almost never have commented on logos, although I've spoken to hundreds of clubs. But this has everything on it, really. It's very globular clusters, Saturn, you know, the Horsehead Nebula. I suppose this is Subaru, Pegasus. No, it's not Pegasus, but Comet. Anyway, well done, whoever that is. Plus, the angle of your coastline here matches this white light here, so you can't do any better. So how have we managed to discover so much about the universe when we've just left home, right? The other test I want to do is just make sure that you can see my marker here. Can you see that? Did you see me annotate this screen?
No. I don't believe.
Oh, geez. I've never had this.
All I see is all of us together on here. I'm not seeing your screen.
Hold on. Let me see if I can pin you down and. Oh. Yeah, there's a. Yeah, I think it's just showing your camera and set. In order to see your markers, you would have to share your screen. You follow?
I thought I had, but okay. Let's.
So right now it's just sharing your video feed. So it's.
But I was sharing till a moment ago. But let me try it again. Maybe there was something weird going on. So there's a video feed. So you're seeing that feedback video.
Yeah, that's your screen.
Okay.
Yeah.
So now when I bring that up, are you seeing my PowerPoint show?
Yes.
Okay.
And now I can see your marker. Yes.
You can see my mouse?
Yep.
And the last thing is, can you see that marker?
Yes.
Great.
All that's fine.
Okay.
We're not seeing your smiling face, I'm afraid.
That's okay. Oh, that's okay. Probably it's better off that way for most people.
I'm guessing at this point you're no longer smiling, so it all works out.
No, I'm blushing at the rookiness of what I just did. But anyway, let's get started. You know, how have we managed to discover so much about the universe? You know, we really haven't left home at all. So images can show us the universe in 2 dimensions and give fleeting glimpses of a 3rd dimension. And of course, that's a cutout from an object eclipsing this that's closer to us than the sun. So if we watch for a while, a 4th dimension, time comes into play. And I hope you can see that some stars are going on and off there. I don't know how fast the platform is, but if you spread the colors out, you get an as-if 5th dimension. And not only is it gorgeous, I mean, these are nature's colors, right? There's no Madison Avenue, advertising designer who chose these colors. And those breaks in those gaps are like a barcode for stars. And they can help us understand an enormous amount about stars. You can see a list there on the various things. Somebody's not muted and was typing, which is fine. It's just if you can mute yourself, that'd be great. About 70, 80, 60, who knows, some huge percentage of the reason I keep pausing here is I've given this talk so much, I keep finding myself leaning into the camera, talking to the camera. Even now, as I'm saying that line, I'm gesturing with my hands. This is going to be good. I'm going to have to get my Barca lounger down here, and I can really rock back a little bit and chill out. So because so much of astronomical research is done using spectroscopy, it's useful to know about it, even if you don't do any imaging, even if maybe you're even just an armchair astronomer, but you probably read things now and then, whether it's on the web or in magazines. And to know what those concepts are and how the data was captured, even if it's just from a talk like this, has really deepened my experience. And I think you also, as an armchair astronomer or a non-imager, will get a lot out of this talk. So I realized earlier this year, I suppose, I was going to say a few months ago, but earlier this year, that I had some agenda items, some things I wanted to communicate. And rather than just sort of trying to subtly lay them in, which I'll still try and do, I've also got them here so that I prompt you, or so you can anticipate where I'm headed. Now, again, that top line here and this number 10, if you're not an imager, fine. Still a lot of this will apply to you. You might want to capture star spectra, though, if you remember that thrill of the first image you captured. For me, and many of us, it was the moon. And it was overexposed, blurry, somebody's mic's not muted. And yet still, even with the poor quality of it, it was the most gorgeous image of the moon I'd ever seen. And I was showing it to my wife, friends, colleagues, they're all starting to roll their eyes. But that thrill fades. And I found when I got into spectroscopy and the fact that it was so much easier than imaging really brought that thrill back to me. You might want to do some science with your equipment and don't know quite where to go. I was never, to be frank, a photometry person, the things that the AAVSO has mostly done. It just didn't interest me. It was putting dots on a graph. But this is very different, as you'll see tonight. You probably, like most of us, don't want to take a big risk going in. And I'll show you some really inexpensive ways to get started. I think this is the most important piece, and is, for me, the most significant piece anyway. When you own the data, it's a very different experience because you naturally are more curious about it and the basis for it and the science. And with Wikipedia and Google, you can now find things and learn as much as you care to about the objects you're looking at. And so some of it you'll actually remember. A lot of things, especially for most of us in this meeting, I think. Maybe not Coy, he's a little younger. Things get harder to remember, but when you've got that stake in the ground of it's on data that I captured, that changes a lot. You don't have to drive to a dark sky site, and this is where Scott's going, oh, that's why he was asking about our dark sky site. It turns out spectroscopy is a lot less affected by light pollution because we're not looking for all that careful, gorgeous color balancing that happens in visual imaging. And he was telling me, Scott, was that your dark site is the road on the road by the levee, and I thought that was really had something to do with a Chevy on the levee, which sort of dates a lot of us if you know what that reference is. You thankfully don't have to have a PhD in astrophysics. I don't even have an undergraduate degree in science. But the cool thing is, not only is it easy to understand, but there's a huge community of people, as well as online resources and books that are many of which are linked from my site, that help you learn as you go. But there are no tests, there's no final exams. You just learn as much as you want. I'm going to sound tonight like I know a lot, but trust me, this is like you look at a river and you go, wow, that's a big river. And sure, it's broad, but it's really shallow. That's me. So not in personality type, in scientific knowledge. So like I said, I wasn't a great imager, and you'll see things I'm going to show you in a minute or 10 done with a video recorder, like with a ZWO camera. So, quarter-second exposures. Sure, you can go deeper and dimmer, but there's tons to do without a lot of skill, fortunately for many of us. I break just about every piece of equipment I use. Control Z and edit undo are my favorite commands in Windows. So I'll show you something that's just totally turnkey. I know you do outreach, and Scott's going, oh, that's why he was asking about outreach. It sounds like you do some pretty cool outreach there now. And I want to, first of all, just thank you all for that. I think that's a way that we pay it forward and pay it backwards. And of course, we've all had enormous opportunities and privilege in our lives to get to where we are, that a talk like this is something we're interested in, even if for just the first 3 or 4 minutes. But truly, I know you took advantage of those opportunities, as did I, and not everybody has that in them. But the outreach is our way of giving back, I think. Mentoring. Here's the thing, a lot of Scott, you were talking about how at some of these big events, people talk about how they used to do astronomy and they sort of know a little bit about it. What I'm going to show you, and I'll point out some of the screens, is the kind of thing you can do live at outreach as a secondary tool. After the gangbusters like the moon and Saturn and Jupiter and stuff, or even M13 if it's dark enough, but or even darker maybe. I think that what I've found is the population generally, depending on the education level, which is generally the socioeconomic level of the community you're in, people know about this stuff. And when you start talking spectra, they'll go, oh yeah, wasn't that in that Cosmos series by Tyson? And yeah, then they'll actually know the episode it was in. So there's lots of opportunities there. And also, you might want to capture spectra if you want to hang out with a cool crowd, which is not me. That I'll own up to. But there are thousands of people doing this. So I'm not showing you something that's, leading bleeding edge. This is a common thing. It's all been worked out. And as you'll see, relatively easy to do. Let's talk a little science for a few minutes just to get everybody to the same level. Sir Isaac Newton split white light through a prism and discovered that the component colors were split out. You can also do that by, let me tell PowerPoint, I'm not used to using my mouse as much as I'm going to use it tonight since I don't need to gesture. If you bounce light off of a finely lined surface, you get a rainbow. You can also pass light through a finely lined piece of glass, and split the light with what's called a diffraction grating. And we'll see examples of that tonight. So Bunsen invented the Bunsen burner to burn a sample and split the light through a prism and observe the result. And he was a real pyromaniac. He burnt everything he could find. And fortunately, he kept great records. And those records are really going to serve us, as you'll see in some of the examples in a few minutes. This guy, Kirchhoff, we won't talk very much about. He was a contemporary and colleague of Bunsen's. But there's one thing on this next slide that I'd like to show you. And that is, there are two different types of spectra. We'll see examples of both tonight. This isn't very technical or scientific. Some of them, these absorption spectra, they have just gaps. And then in the background, they have a rainbow, right? And red, orange, yellow, green, blue, indigo, violet, Roy G. Biv. And then the other type of spectrum is an emission spectrum where the background is black and they're just bright lines. Now, which you get shouldn't bother us for now, but it depends on the temperatures involved in creating the spectrum. So that's all we'll talk about Kirchhoff for. So, but these spectra, when you look at them element by element, differ. So, for example, this line in hydrogen, this emission line, doesn't exist down here in helium. That's weird. So, in fact, hydrogen is so common in the universe and so easily used that we've given these lines in hydrogen a name, the hydrogen bomber lines or series, and actually given them Greek names, much like we give names to stars in a constellation by brightness. This is by color. So, for example, this hydrogen beta is here in, sort of this robin egg blue or so. So we'll be hearing a lot about them in the next few minutes. Here is a cool periodic table. And I just want to look at hydrogen with you for just one moment. There's a hydrogen alpha. There's a hydrogen beta in the aquamarine. And there's a hydrogen gamma. Notice that all the other lines are different. For example, helium, like the helium you'd put in a balloon that you blow up in a flower shop or a grocery store, has very different lines, as does lithium here, which is the lithium that you'd have in, for example, a cell phone or laptop. So we don't have to burn things anymore. This is actually a gas tube, and this is my software running with a little tiny tripod-mounted camera that I created a couple years ago, or probably 4 or 5 years ago now, for classrooms to study spectrum. This is a hydrogen gas tube. So there's the hydrogen alpha, there is the hydrogen beta and the robin egg blue, and so forth. And we'll look more into this in the next few minutes. We're going to jump around a little bit. I want to move real fast to get past all this really relatively short science section. In 1835, this French philosopher said the stars are just too far away for us ever to really know much more about them. But it wasn't a few decades later that people were studying the stars and knowing a lot about them with spectroscopy. You know, Comte didn't know about spectroscopy and what it would deliver. Nobody did back then. Sometimes I think about, well, what will it be in 30 years from now that people go, wow, you know, that's right, back in 2020, they didn't know that. Will it be in life sciences? Will it be, who knows what, quantum computers, which we know a little bit about now. So far, every astronomer I've shown has been an old white man. So I want to show some of the other contributors, big contributors to the field. One of the oldest ones is Annie Jump Cannon. She and her computers, which was a team of women, were prohibited from accessing the telescopes at Harvard because of their gender. So what they ended up doing was studying the glass plates made from the spectroscopic film. And they were really good at it. Not only just studying them and classifying them, but they actually, because they looked at literally hundreds of thousands of these plates, and they were able to come up with a coding scheme that replaced the unworkable one that came before them. It was really an ingenious amount of science that they did. Priyamvada Nataraja is at Yale. She studies hyperactive black holes. Nancy Grace Roman, you may have heard her name, and this is the Hubble Space Telescope behind her. She was the first astronomer at NASA. She got her PhD in the late 1940s. What an accomplishment then, given the climate. She was a proponent and a big visionary for the Hubble Space Telescope. Thank goodness she pushed to make it happen. Elisa Quintana studies exoplanets on red giants, and Jedediah Eisler's at Dartmouth. and she studies gravitational lensing in black holes. So there's an overview. We've made a little bit of progress. This is a fun slide to put together this summer because I discovered so many other women who I just had never heard of before. So we've come a little ways. We have a longer ways to go, but we're making progress slowly, unfortunately. So how do we get those absorption and emission lines? Well, the Bohr model is, as you may recall, is these orbits for electrons. So there could be an electron sitting there, and when it drops down a level, in this case from level 5 to level 2, so it's more than one level, it gives off energy. And that energy can be visible in certain cases. And so there is the color of that transition. This is a hydrogen atom. Let's look at a different transition from level 3 to level 2, and you can see there's another line. And finally, this one, which, let's see, this is level 4 to level 2. We'll keep that in mind. That's our robin egg blue hydrogen beta. So what if an electron jumps up? Well, then we get that different spectrum. Instead of it being the emission spectrum, it's an absorption spectrum with a continuum in the background and a gap. Okay, so we'll see examples of all those tonight. Now, there won't be any quizzes on this. It's just a little background for you. So the Hubble spectrograph was serviced by the space shuttle some years ago. This is that process. My teenage son says that isn't a refrigerator, or it isn't a, I blew the line. That's not a scientific instrument. It's a refrigerator. And he says it's filled with beer, and that when it's dark on the space shuttle, they were big party animals. And, you know, they get a lot of dark, during a 24-hour period since they're orbiting the Earth. But he knows better, but it's a fun story. Here's Dale Mays. You can see a really complicated device there. But I want to talk tonight, and I'd normally be waving in front of you, but this picture does the job. This is an 1.25 inch grating called the Star Analyzer. It's got those little grooves on it like I was talking about earlier, like the grooves on a DVD, but it's a transparent piece of glass, and it splits the light. So here's a cool example to get us started. So this is the grating on the nose piece of a DSLR. 30-second exposure got us hydrogen alpha, hydrogen beta in the robin egg blue, and hydrogen gamma. So notice it doesn't even have any tracking. So this, I show this slide not because I suggest this as an approach, although it's inexpensive if somebody's really strapped for funds, but with the small aperture of a DSLR, and more importantly, without tracking, it's a real challenge. I'd love to be able to tell high school students, just get your parents' DSLR and buy a grating in my software, and you'll have a cool science project. And it's true, it is a cool science project, but not without tracking. It's just too hard. Remember the challenges you had in finding stars initially, and then imagine having to take a 30-second image without tracking. It's doable, but it's not preferable. So here's some examples of the way to mount this grating, and then we'll actually look at some examples of the kinds of things it can do. First of all, this is the one we saw on the previous page. This adapter here is just it's a thread adapter that adapts from the threads on the lens cap to the grating adapter, or to the grating itself, excuse me. This is a FITS camera. Could be cooled, maybe not. This is an example of a video camera I'd be waving in front of you at this moment. And this happens to be a ZWO camera. This is the 178 color, but it could be a mono. And typically the grating, the cool thing is it just threads right onto the nose piece. And we'll talk about that in a little bit too. Here, a grating is hidden inside that filter wheel, so that works too. So there's lots of ways to mount these things. There are more expensive devices. This is sort of a monumental decision I've just made in the last 4 seconds. I think all of this equipment stuff, I'm going to leave till after my talk in the future. People don't need to see this now. You need meat. You don't need the dressing and the accessories. Anyway, you're stuck with this presentation. My apologies. I've given this presentation hundreds of times, and it just occurred to me. I'm always trying to improve it. So this is, you can see an order of magnitude more expensive, and even worse, they have like a 100 micron slit. And so that means you're tracking and acquiring your target on a slit like that. They're a lot harder to use and even to set up and to process. So nobody really starts with these. There's this intermediately priced device that you can 3D print, but it also has the same challenges with usage because it's got a slit. You can piggyback a DSLR on your telescope or mount the grating on your main telescope, prime focus down here. Oh, so what can we do? We're done with all that stuff. Sorry that it took so long, but I think that you'll really appreciate what I'm going to show you in the next say 25, 30 minutes. So you take a star, you put its light through a grating, you get this star and spectrum. There's a cool example. This is like to kick things off. It's done by this guy Torsten Hansen with an 8-inch Newtonian and an imaging source video camera, much like a ZWO. These are all different images taken at different times in temperature order. So these are B stars here, and then they get cooler and cooler down here until type M stars and K stars here. So, I mentioned earlier that you can use spectra to tell star temperature. You can see a fantastic example of that. Notice how the cool stars look if I can find my mouse, look very different than these hotter, let's say B and A stars. So I'll look at with you just two quick examples here. One is, notice that thing. That's like a forest of lines, right? It's not single lines like we're seeing up here. It's called a band, and we only see these on cooler objects because those are from a molecule that are in the atmosphere of the star, and the star are in the outer shell. The star is cool enough that it doesn't incinerate the molecule. It happens to be titanium oxide, but that's a deeper level of understanding, and I don't go any deeper than that. I don't know what titanium oxide is used for. One of the titanium oxides or dioxides is used in suntan lotion. So this area here is the only other area I'll show you on the screen, around 4800 in the robin egg blue area. Notice how this line or a gap is much darker on the type A stars. Now remember, these lines are caused by electrons jumping from level 4 down to 2. Well, these hot stars up here are so hot that, for an electron to get up here, it has to get pumped up there. And these stars are so hot that the electrons, when they get pumped up, go right past level 4 onto higher levels or even out. And so these lines aren't as strong because a lot of the electrons don't even land on level 4. So similarly, these cooler stars, a lot of the electrons don't even make it up to level 2. They're just not hot enough to pump the electron up to here so that it can drop down, or it would have to, again, pump it up to here, same thing, excuse me. So it could drop down to here. I'm not quite as fluid as I prefer and normally am tonight. I'm perfectly healthy, but I had a little bit of a COVID scare last week. It turns out just a cold with a flu and a sore throat and aches and pains and the stuff that we normally really didn't think much about, except darn. Well, this was a little more than darn. But the good news is for all of us, if you don't know anybody or yourself haven't had it, the COVID test with a nasal swab is uncomfortable, but it's not like, oh my God, awful. And it's really only 5 seconds in each nostril. So I say that just so in case that's one of the things that's been worrying you about the potential for having to get a nose swab, it's nothing. And I hope you'll remember these words when that time comes about. So now that we have seen a very qualitative view, let's look at that. You see in that crosshair in the robin egg blue area, maybe you can see, I'm not sure I can, there's a little bit of dimming right in there. Well, if suppose I got, I don't know how it would happen, some time on the Hubble Space Telescope, and I studied some object, and this was the spectrum, and I wrote a paper that said, yeah, there was a little dimming when we observed this object with the Hubble right in the robin egg blue. Of course, that paper wouldn't be published, right? So we have to be qualitative to really do science. So what we do is we take this data and we plot the intensity. How bright is that area? So for example, this star is what? Really bright and narrow. So this data here is really high because this is an intensity scale, how bright it is, and it's not very wide. Whereas this area over here, it's pretty dim here, and then it's brighter in this area where that hump is, and then it's dimmer here. So this goes dim, brighter, 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 dimmer, 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 dimmer. So not only that, but look at that. That area in the crosshairs, when we plot the intensity, very clearly shows a dip. That's science. Now we can measure the width, the depth, the location, how it changes from night to night or object to object. Now we're doing spectroscopy and science. And I think one of the big obstacles to getting started in something like this new is the concern about, I know I go, oh no, another learning curve, more software. And
so my story is I got a grading in 2009. As I said, I wasn't much of an imager. It hadn't really captured my attention. And I wanted to do some science. I went outside and right in my backyard here, 3 miles from Pike Place Market in Seattle, and set my C8 up with a webcam where I literally duct taped an adapter, right, a nose piece onto it, and plugged it into my telescope, and played around. You know, it was Saturday night about midnight. I came in, I had some video footage. In fact, this is a frame from that video. And Sunday morning, I tried to create one of these curves so I could do some science, and I failed. I used some of the freeware that was out there, and the problem was it was half in French, it was crashing, there was no documentation, and frankly, it really wasn't at the level of usability that we've all become accustomed to. And so what did I do? I'm embarrassed to admit I quit. I told my wife, I'm supposed to be having fun. This is a hobby, and I'm not having fun. And I tried. So I put the grading in the drawer and figured I'd do something else, but it kept bugging me over the next couple of weeks. So I decided, okay, next weekend, next Saturday, I'm going to write a piece of software just to create this graph. And I did that. And now, 11 years later and say 15,000 hours later, I'm almost done. My wife says, finish it already so we can start having dinner at a decent time. It is finished, and we do eat dinner regularly, but there were a few years there when we didn't. I had a real job as well as this. So I want to show you the software very briefly because, oh, geez, let's go like that. There's the software. There's a frame from that video, same one we were looking at, the star, the spectrum. I prefer color when I'm doing outreach and education because it's more intuitive that, oh, yeah, that's a rainbow. There's a gap there. There's some gaps maybe there. There's the intensity plot over here. There's a peak. That's the star's intensity. And then there's this thing, dim, brighter, 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 dimmer, dimmer, dimmer. And that dip in intensity right there is that gap. All right. You says, and you should, big deal, Tom. There's dips. Now what? And that's what I experienced in 2009. It's like, well, what are all these dips? And you remember I mentioned Bunsen, he created all these catalogs of elements that he'd burnt. Thank goodness, because now we have that data and we can build it into a catalog in the software. So I can come down here to Hydrogen Bomber and say, show me on the graph where there would be absorption lines if this Vega had hydrogen in its outer shell absorbing light as the photons left it. And wow, look at that. We've got dips that are matching up. That's pretty good evidence. And there you can see hydrogen beta. Pretty good evidence that we now on a backyard telescope have detected hydrogen on a distant star. Pretty amazing, huh? I was fascinated and still stunned by it. Now for outreach, a couple things. First of all, you can turn that on to make it pretty. And secondly, this is actually a video, single frame I'm showing you here. Let me bracket in the region we want to study, which is right there, and start the playback of the video I made that first night. So now the image is changing a little bit because of seeing here in Seattle that night, and so our graph is changing. But this is really interesting to everybody. But if you're doing outreach, this is a great screen to have up because now you can start talking about spectra, a lot of which, if you're not familiar with now, you'll learn as you get started because of a couple of references I'll show you, as well as the other sources I mentioned earlier. Now, one really cool thing I just can't not show you, although it takes a minute of time or 30 seconds that I prefer to use elsewhere, but it's so cool. So here, this hydrogen alpha feature, let's see what the hydrogen, look how, you can see that feature sort of comes and goes, right? I think it's more fun to look at this one because you even can lose it for a frame, right? Where you just, well, maybe there, that one, you couldn't even see the dip. But we all know that if we stack images, which we'll do here, it eliminates a lot of the noise. So look at that. At 2 frames a second on our playback, it only took 5 or 10 seconds to get a fairly symmetrical Gaussian curve. So this is the kind of thing you can set up. I prefer not to stack at an outreach event because this jumping around interests people. That's really all I wanted to show you in the software, just that you should see how easy it is to bracket something in and get that graph. And we'll talk a little bit more later about how to identify some of those dips. Okay, let's go back to the PowerPoint show. So here's an outreach event. You can see that actually they're doing a gas tube here, but they were just about to transition to Vega, I think it was. This is in France, actually. So I'm going to show you. In fact, in Louisiana, you may be able to answer this for me. It says, I suppose I'm trying to say this tongue in cheek, but I could be betraying my ignorance also. Département de Physique. Now, what I want to know, is that the gym department or physics department? I think it's the latter, but you know, I don't know. So which is it?
Physics.
I thought so. Thanks for your help. Now I know, and I can charge into that joke or omit it, depending on how shameless I am. So here is. Oh, let me set the mouse pointer to continue to show. Here's a wide field view with a DSLR. You can see 2 stars there, 2 spectra there. There's a gap. Here's a Wolf-Rayet star with some lumps. Those are, again, they're widened just because they're so bright on our sensor with saturation. And these are emission lines. So in fact, let's look at a Wolf-Rayet star. Now I have a confession to make, and this is a true confession. When Janet Simpson sent me this, I couldn't remember what a Wolf-Rayet star was. You know, I'd read about them like many of you, a handful of times or more over the years. And I just couldn't remember. Well, Wikipedia is your friend. They're supermassive late stage stars, probably heading to be a supernova. They're like 25 times more massive than the sun. They have intense stellar winds. So some of the outer shell has been dissipated. And this is what their spectra look like. So here we can see wide emission lines and carbon, carbon, carbon. Why would we be seeing carbon? Well, remember, stars burn through different elements, right? Starting with hydrogen and then helium. And carbon is along that pathway. And so we're seeing some of the late stage fusion that's going on with this star. These are really wide here because of the intense stellar winds, which broaden the data. We'll see more about other kinds of broadening in a minute. So here's another emission object, our beloved Ring Nebula. It's a little different when you look at it visually through a grating. Fortunately, there are only 2 elements. So we have hydrogen alpha, and this is ionized oxygen. That's what that Roman numeral 3 just means, that it's ionized and electrons have been pulled off. So typically, an extended object as opposed to a point source isn't going to look all that good in a slitless system. But this is one example where they do, and we can see those 2 elements. Let's look at another beloved object with the emission spectra, and this time with a slit spectrometer. Certainly non-compact extended object, right? And notice there's our ionized oxygen with its Roman numeral 3 and our hydrogen alpha. So this is a great example of how much improved a slit spectrometer makes our spectra on extended objects. Now, my first experience with M42, in fact, for just a moment, think for yourself, or consider to yourself, when you first saw M42. Maybe it was at a star party, on trying to find it on a Tasco in your backyard, or on wherever. Mine was at a star party in the early 1990s. Shoemaker Levy was coming. I wanted to do astronomy. I was living in Denver. I went downtown to a first quarter star party, and it's fun to remember when you didn't know something, you were ignorant about a fact. Because when I walked out on that observing field, it was well lit. It was in the city. What I saw, those cannons that they use in the circus to shoot people out. Well, and actually there was a guy on, I'm embarrassed to admit, I've never told this in a talk. There was a guy on America's Got Talent who did that not long ago. That's what I thought I was seeing. I'm going to myself, what are all these cannons doing here? I came here to see telescopes. Of course, they were Dobbs, and somebody like some of you and me were, standing by the Dobb, explaining what people were seeing to whoever was at the front of the line. I queued up. I was all excited because, I'd seen glorious photographs like this one. And when I got up to the eyepiece, I think you probably get a sense for where I'm headed. I was really, I was going to say crestfallen. That's too dramatic. I was just disappointed. It was a smudge. There was no color. It was barely seeable. It had no size. Well, I didn't know any better. But still, here's the reason I tell that story is because, like some of you who may have experienced that, I still go out and look at M42. Why would I do that? Well, first of all, we've all gotten a little better at averted vision and can see a little more detail. And our brains have gotten better tuned at processing weak images. But more importantly, I think the reason that most of us go out and look at M42 now is we know what it is. We understand that, it's a stellar nursery, it's, birthplace of stars. And so the point is, when you come to the eyepiece with understanding, with a little bit more understanding of the object you're observing, it really enriches your experience. So for me, spectroscopy has done that. And that is, when I go out and visually observe, I understand more about what the star is and what we know about it and how we learn that. So I say that, I'm really not necessarily selling you software or grading. I'm just selling you on spectroscopy. If I sell you on you're doing spectroscopy, that's my goal. So here are the spectra of Uranus and Neptune. You can see these gaps here, and you can see there the intensity plot of that gap there, or maybe it's that gap. That's a pretty wide one. So this is the methane on these two planets. We're actually observing the atmosphere, and whether it's discovering potential life in the atmosphere of Venus, or whether it's finding ET, finding an exoplanet that has some sort of life perhaps, or even the reason I just paused there is somebody asked a question the other night about using spectroscopy on Mars, and I was really happy to be able to point out that the rover on Mars had that arm that pivoted up and had a camera on it. It also had a laser that would burn a piece of rock or a sample in the distance, and it had a spectrometer that would capture the spectra. So much like Bunsen was burning things, we're still burning things and capturing spectra, 150 years later. So it's a fun story. So in 1881, Henry Draper, that's the Draper catalog guy, captured the spectrum of a comet, and it was an important story in its day. So listen, hey, if Hank can do it, so can we. So there is a spectrum of a comet, beautiful little string of gems, isn't it? And there are the emission lines called the carbon bands or swan bands, carbon lines of this spectrum. And this was captured by a guy named Vikram Agnihotri. He's a nuclear power plant engineer in northwest India, in Rajasthan. In 2013, he was a rank beginner, and now he's really an expert. I learned from him, and what teacher wouldn't like to learn from their student? That's the best outcome. So here's a more contemporary example. You can see this peak here from the sodium lines on Neowise, and this was done. This is an objective grading, means it's just a DSLR with a grating on the nose piece. So there are interesting objects, especially if they're bright, that you can capture spectra of with just a DSLR. So anybody who uses a C-clamp on their equipment, that's my kind of observer. Of course, my problem is, as I mentioned, I break things. I'd probably torque down the this surface a little too tight, and I'd buckle the box and destroy the instrument inside, which in this case is a video camera. So Robin Leadbeater fortunately didn't do that. He put a star analyzer on the nose piece. He's a designer of the star analyzer and expert, still really, really helpful to our community and me too. He's on our forum and answers questions all the time. This is a single frame from that video, so the great straight line, not. The meteor traveled that distance in one frame. This is the meteor itself, and that's its spectrum. You can see the gaps or the lines. So for example, that gap there, now that I've hidden it, is that dip there. So, and here you can see the elements that he was able to observe. This is somewhat harder than star spectra because, you got a moving object and you got to capture them. You can sit and wait on the Perseids, but that doesn't happen very often, right? So, but this is like a field some people love and get into. So I'm not going to talk much about the sun tonight. We've heard a lot about it over the last 2 years, and we'll be again hearing about it as the next total eclipse comes up. The one thing I wanted to mention is in 1868, when they observed the sun in eclipse, so, Bunsen was probably still alive. I don't know when he died. And I won't say that again in a talk. Next time I'll know. So this is a sun, and it is an extended object, but during an eclipse, it's just a compact, narrow thing, so you don't need a slit. And they said, what's this yellow? Bunsen never burned anything on the Earth that had a yellow emission line at about 5,800. We don't know what it is. Well, let's give it a name because we have a physical property for it. We know that it's a yellow line at this wavelength. Greek for sun is helios, so we'll call it helium. That's all we knew. That was it. Now you fast forward 40 years, and forgive me if you're familiar with this story, and a couple of researchers independently were studying a gas that they had created, and they found a yellow line just like this one at exactly the same wavelength in angstroms. That's the unit of measure for color or wavelength. And they said, Eureka. That's pretty corny, isn't it, for me to say? They said, Eureka, we just found an emission line on a sample here on Earth that matches an emission line we saw on the sun, 93 million miles away. We just discovered helium here. I love the story because it shows really clearly how powerful science is. So if you have friends who are doubting science in any way, this is a great example to show them how science works. I don't know if anybody gets convinced of their closely held beliefs these days, but you can give it a try, as maybe some of you have tried. So DSLR spectra of novae, you can see this one has a deep dip for iron. This one doesn't. Again, talk just a moment about Doppler shift to remind you. If you're moving towards something, the waves are as if squished together, and so the pitch is higher. If you're moving away from something, the waves are somewhat stretched out as if, and the pitch is lower. That's why a train whistle going through a station goes, right? High coming towards you, low going away. Frankly, you can do it tonight in the car or tomorrow morning. When you drive past trees in the car, if you have a window down on the passenger side, you can hear those trees go, right? I haven't figured out how to do that quietly yet. Whispering doesn't let you change the pitch very much. So that's how Doppler shift works. Now, suppose we were expecting this triplet. I love the word. It's almost self-explanatory. Expecting this triplet right here in the yellow, but instead we saw it over here. What would that tell us? That would tell us that the object was moving away because it was red shifted, right, towards the red. And if the triplet was shifted over this way, it was blue shifted, and it was moving towards us. Let's look at a great example. There's lots of different ways stars blow up. Supernovae, there's one particular type called a type 1A. And this is when, I'm not going to get into a lot of detail on this, we don't have time. This is when a large gassy star dumps some gas onto a white dwarf, and when you throw gas onto something hot, it blows up. Here's an example in M101. There's the supernova, and there is an image of a different type 1A. It's not this one, but you can see that it's really got a spherical shape to it. And this is the spectrum captured by David Strange with a 9-inch telescope in less than 15 minutes of stacked images. And there's the intensity plot. Can you see that little dip there? Well, there it is in the graph, really clear. That dip, the giants have told us on whose shoulders we stand. They've told us if there's a deep dip just above 6,000, that's a type 1A supernova with these two stars. This a pair of stars that are binary stars, not a pair, that would be four, binary stars circling one another. And this won't be on the quiz, but I wanted to show you here for type 1A, the one we're looking at, look at that deep dip that they say should appear at about 6,000. That's silicon, and that's a type 1A. Look at these other types of supernovae, single star typically. Type 1C, 1B, type 2, we're not going to talk about them at all, but they don't have a deep dip in this region. That's how David Strange was able to identify this as a type 1A supernova. Of course, it had already been identified that way by the time he got to it, but this is one way that amateurs can contribute to the professional community, is they can help identify supernovae with spectra like this. The only fly in the ointment is we get so few supernovae in our galaxy that the ones we see are typically far away and really dim. But there are typically, several a month, I suppose, that you can look up on a professional site and actually get your name included in various records and publications. So you may, I wanted to show you this. So David and I measured the wavelength of that dip. We noted it here. We noted what the wavelength would be. We looked it up on the web if Bunsen had burnt beach sand. And then Wikipedia was my friend. I couldn't remember the formula. And fortunately, it was just a division and a multiplication and one subtraction. And when I plugged the numbers in, we were able to calculate the blue shift of this shell expanding towards us. It's really moving fast. You may recognize Adam Rees. He's the one who got the Nobel Prize for work he and his team did just before the turn of the century. And they basically were studying the cosmological expansion of the universe accelerating, and he used type 1a supernova as standard candles. So the reason I was pausing is I thought I had a note to make here. We'll go and look. Maybe it's on the next slide. I couldn't find it on my other screen. What about the spectrum of a black hole? Well, of course, black holes don't emit light, but the matter circling and spiraling in goes very fast, gets very hot, and creates an emission spectrum. David Hayworth in Portland, Oregon, looked at this quasar, and there's the quasar. I've never observed it myself. There's the spectrum. You can see two little dots in the spectrum. There are those dots. There's the spectrum. This guy now I do want to look and see if I can find my notes, because I had something interesting. You don't see it here. He was 25 years old in the mid-60s. And I read an account. It's fascinating. It's a transcript of an interview he gave about this discovery. It's linked to on my site, and I'm happy to send it to anybody who requests it on our site's contact form or via email. He was really frustrated. He couldn't figure out what these peaks were. So he said, I'm going to go back to square one. So he figured, let me just prove, and this is a lot of what science does, prove what they aren't. So he said, let's prove they're not hydrogen. So he brought up a hydrogen series, and you can see here, this is the one I wanted to have you keep in your mind's eye from my software. This happens to be Vega, but we can see the reference lines for the hydrogen series. There's a hydrogen beta in robin egg blue. And he went, okay, there's really no matchup between these. So we're not looking at hydrogen, whatever this object is, except it was hydrogen, massively redshifted. So redshifted that he was able to calculate using the Hubble constant or the redshift, its distance or speed. And this object is about 2 billion light years away. It's amazing that light coming from that distance and time still has enough information in it that we can tease it out with a backyard telescope. So that light didn't really age very much. Humans don't age quite as well. This is Martin Schmidt a few years ago. I've been rightly accused of throwing rocks in a glass house. If you remember my video image from before I gave this talk, I don't have any hair. He's got a full head of hair, for God's sake. It's okay. I'm envious of the guy. Okay, 2 more examples and we're done. So far, we've been studying these hydrogen alpha features. Suppose we wanted to zoom in on that feature. We can't just use our mouse wheel, right, and just scroll in. That would be like adding the empty magnification when we're trying to see more detail on the moon, right? At some point, more magnification doesn't get you more detail because of the optical issues. So what we do for this is we use one of those slit spectrometers. And here's an example of the moon and Vega. And notice this is the hydrogen alpha feature. Notice, first of all, how much deeper and clearer they are than on our grating, but also notice their offset. Now the moon, this blue one, isn't really moving towards or away from us very much, but clearly Vega is. And we measured here on this really quick spectra that we estimated the radial velocity was 20 kilometers per second, and the published value is 12 or 14, I see. So this is the kind of thing that you can do. So I'm not, in fact, I am, even though it's going to be weird, because I want you to see me. So I'm going to try and figure out how to stop my screen sharing in this mess. It's down on the bottom, you say. Help! Okay, let's move this over to the other screen. There we go. And now stop sharing. Oh, there it is. Okay. And we'll move this back. So can Scott or Coy unmute yourselves? Can you see me? Or shake your head, yes, thanks. The thumbs up works. Now that I can see some of you. So here is a star that's rotating very quickly. I wish I was a Harlem Globetrotter and I could spin it really fast. That would be a great finale, wouldn't it? So this edge is coming towards you from the rotation, right? So that light is going to be blue shifted. And this side is rotating away from you. So that light's going to be red shifted. Whereas this surface here from rotation at this particular point isn't really getting any forward or backward speed because well, it just doesn't have that speed. So what would that spectrum look like? So now we're going to share my screen again and get that noisy thing. And let's pop up the slide before it drives us all crazy. So what's happened here? Vega doesn't have that dip, but Altair doesn't have that broadening. Look at Altair. Look how much flatter it is. Well, that's a rotational broadening. So some of the light that would normally be here ended up getting smeared out here towards the red, and some of the light that would normally be here got spread out towards the blue. So a lot of this light was basically stolen into the wings. That's why this is flattened. This as well as the preceding spectrum were done with slit spectrographs. This is a remarkable example to me. These people are so brilliant. You know, it's such a simple idea, and you know the information it shares is just remarkable. Okay, let's finish up here real quickly. I'm sorry I've gone a little long here tonight. What do you need to get started? You need a grating. You need any sort of camera, color, mono, fits, cooled or not, DSLR. You may need a spacer, and that's because the distance from the grating to the sensor, it's not like it has to be exact like when we're focusing, but you don't want it to say too close and you don't want it too far away because you won't get a good spectrum. And so there's a calculator on our site, and I spend a lot of time helping guys and women who send me their kit and you know their specs of their setup and their camera, and I plug it into the calculator and I tell them whether they need, oh look, we need to get that mouse back again. I tell them if they might need a spacer, they might need a shorter eyepiece, but many cameras you just thread it on. Typically the ZWO cameras are like that. Bigger aperture may need a focal reducer, which you might also well have already for other imaging. There's plenty of books out there, great books. And that's all I'll say about this. I did have a visual example, but we don't have time to show you. The software can be downloaded from my site for 30 days for free. And the AVSO has jumped really big into spectroscopy. Both Stella, they're a great director, as well as Arnie, her predecessor, are professional astronomers. They understand the value of all this. In fact, I spoke to about 400 attendees in August, and we'll do another session in November. You can find that on our site, on their site. The cool thing is, about 4 years ago, I did an hour-long in-person workshop to the AVSO assembled members. There were about 1,000 or about 100 people there, and they recorded it. So it's available on YouTube. So if you download the free version of the software and the sample data that's on the same page, you can then play that YouTube video from that workshop, and in an hour or two, you'll know enough that not only could you get started, but you'll know enough, even if you never plan to start, that you'll have spectroscopy well, I was going to say in your bones, but I could also say, also under your belt. So there are pro-am collaborations possible, not as many as we hope to see in the next few years as the AVSO ramps up. They've got a spectrum database now. These are all amateurs there. So we've come a long way in the last almost 60 minutes. I really apologize for running a little late. I hope that you found the time helpful. I hope that you laughed at some of my jokes, or at least smiled either at the joke or at me. Either way, I don't mind. It's fun to have people laughing. I want to thank all of you for the fun time tonight that I hope you had, and also for the outreach that you do. So if you've got questions, take it away, and I'll do my best to answer them, either here or in the future. You can contact me on the website. I spend most of my time, which isn't a full-time job, but most of my time actually helping newcomers, explaining things. They send me samples of data they collected of images, and I make a little screen recording and explain what they saw. But so if you're interested, whether tonight or some other time, don't hesitate to ask questions if you've got them. Some people are a little shell-shocked or a little drenched from drinking from the water hose I just sprayed for 6 minutes. My apologies. But I'll shut up now and let you all carry on. Go ahead.
Thank you so much, Tom. That was great. I will say the subject has come a long way since I was using a mass spec in organic chem back in the 90s. Wow. Doing organic chem, we did a lot of experiments, but I'll tell you, the one I remember is when we used the mass spec, just because it was this weird, kludgy looking object that we're like, how do we use this thing?
Yeah.
But what I love about the subject is it bridges multiple disciplines. If you're biological sciences, if you're chemistry, if you're physics, we all use this data. We all understand the composition. And so if we do outreach, or if you meet somebody that's in any science, you can talk to them about this stuff and they will get it.
Yeah, the greatest new users are the ones who say, "Yeah, I was a chemist for my career. I'm now retired." I go, I'm home free. This is not going to be support intensive. No, and generally it's not. I probably talk to or email with 1 in 20 or 1 in 50 of my customers. It's and that's not for very long. Usually they fly out of the nest and then they go off on their own. They sometimes post on our forum, which would be also an interesting place for you to read. That's a really great observation, Coy. I hadn't thought of it in the way that you just spelled it out. I may incorporate that into some of my presentation too.
Well, what blows my mind is they're doing this in high school now.
They are. Yeah. Well, in fact, I mentioned this really briefly, this we sell to a lot of chemistry and physics as well as astronomy educators. And one of the really cool projects when you talk about multidiscipline is the University of North Texas. They have liberal arts students in Astro 101 capture spectra of a few gas tubes. Oh, and now I can show you what a gas tube looks like when it's running. But, it's not all that big a deal. It's just I think I'll turn it off since it is high voltage. This is a helium gas tube. So they capture spectra of a few gas tubes, and then they go outside and there's a TA operating a C8, actually 5 C8s. And the TA is pointed on Vega with for themselves hydrogen.
Live streaming is on.
Oh, it's on again. So good. So they all missed that little bit of the story. Our apologies. The cool thing about this project is they run 2,000, it's mind-blowing, students a year through this lab. So anyway, what about astronomy questions? Anybody have any imagers here or capturing images today? All right, well, that's fine, but I know you all do outreach. That's okay. No apologies, Chris. You can still do outreach with this easily.
I did want to say one thing. You had a picture of Dr. Reese on there a while ago.
Yes.
He shared it with Dr. Perlmutter, whose team designed. Well, one of our members that we mentioned in the beginning, Dr. Brad Schaefer, was on Perlmutter's team.
Really?
Yes.
Oh, that's fascinating. That's really interesting. And in fact, go ahead.
He came back. He was sent promoters paid for his entire crew to go over for the award to him, paid for everything for everyone like this. And Brad came back and showed us the gold embossed invitations, pictures, everything from the ceremony and everything on there. It was fantastic. But I just want to mention Brad was with Perlmutter while you had Dr. Reese on your presentation.
That's very cool. I'm looking at my notes for this slide. It was one of the things I was looking for. I do have Perlmutter's name on it on my speaker's notes, but I generally it's frankly it's just a mouthful to say. It's unfair to him not to give him credit too. But what I don't know, and I've always hesitated a little bit when I tell that part of the story. I don't know if his team. I don't think his team got anything. It was a high. What do I say here? It was the high B team. No, it was just the two of them. I'm hoping things will change a little bit in the future. Ben, it sounds like you're familiar with the story too.
Yeah, well, they for the Nobel Prize, just the team leader is awarded the prize, but he was a partial recipient of the Gruber Prize?
I think so. Yes.
Yeah. So they won that first before the Nobel Prize, and that gets spread out to each team member.
Well, I'm glad to hear that. I think especially in terms of women getting more recognition, I think we're going to see more and more teams sharing notoriety, and I hope the Nobel Prize Committee will also do that. The part of that story I didn't tell because it was just running late, but this is more entertaining and not science. That interview with him, the reason it was fascinating was a little bit of the science, but more importantly, his personal observations on his experience. First of all, he was really scared when he figured out that those were hydrogen lines so red shifted because it was such a simple solution. And he describes going down the hall and talking with other people in his group, and probably Perlmutter was one of them, and just being worried. And he says, actually, in this interview, I was worried that I was like so wrong that when this got published, somebody would, point out my mistaken thinking and say there's a much more clear explanation, and you're just so wrong about this Occam's razor and everything. So, but then he says he went home and he told his wife, he said, something terrible happened today because he knew what the fame was going to do for him. And then he had some other researchers with him, and they broke out some champagne or some wine or something to celebrate because they realized how big a deal it was. And the bigness, and I think both of you, with your familiarity, John and Ben, know this. The big part of the discovery was that an object could be 2 billion light years away, and yet to us still seemed so bright, which meant intrinsically it was enormously bright. And I forget, I was just reading something about if it was as far away as one of the close stars to us, it would be as bright as our sun. There's just some mind-blowing way to try and capture the order of magnitude of brightness it is. Other questions?
I just want to mention that you said a minute ago that Promoter had his whole team and Reese had the whole team. They did it separately, but they came up with the answer at the same time.
Oh,
that's why they shared it.
Oh, okay. I didn't know the details there. Wonderful. The other Adam Reese story I have is that I'm dating myself now. In 2011, when I had my first article on spectroscopy published in Sky and Telescope, I had that quasar example. And in my text, I said, this is Doppler shift. And so Robert Noye, who was editor-in-chief of Sky and Telescope, he knew the answer to this question, but he wanted backup, I suppose. He sent an email to Adam Reese, who as yet had not won the Nobel Prize. And apparently he had the contact, or maybe they were friends. And he asked Reese, he said, is this Doppler shift? And Reese responded and said, no, it's not Doppler shift. Even though there's cosmological expansion going on, nothing's moving. And that's really an interesting use of the language, very precise to say that cosmological expansion isn't moving. Again, I'm not sure we all need or anyone needs to be that precise, but certainly professionals do, and he did it. So we changed the word to cosmological expansion, redshift. I think we used instead of Doppler. Anyway, another story. So, what else?
So with your like I have a little camera. I have a little Malin cam. Similar to the ZWOs or whatnot.
Sure.
If you, what's the process that you go through? Like if you have that rig, I put the little filter on there, and then I would capture the video with my regular capture stuff, and then use the other program to analyze it.
Well, there's two ways you can do it. My program will read DirectX cameras, and many of the Malin cameras do have working DirectX drivers. So you could download, or if you got the software, regardless, you could confirm that it works DirectX, in which case you can do live spectra, much like the example I just showed. Otherwise, you'd use whatever camera control software you're using, like SharpCap, and then create an AVI and then pull it into the software. So it's pretty straightforward. I had another quick video to show you. People who would just go ahead.
The software. So the software has camera control capability.
Yeah,
already. Okay.
It does, but it's only DirectX camera control, and in that case, you get what pops up. And the way DirectX is sort of cool is it pops up the camera control screen that the vendor wrote into their drivers. So as a developer, I don't have to know how many controls and what their range of usage is or any of that. Writing camera control software is a big project, and I've never wanted to reinvent the wheel. This is a hobby, So the couple quick screens, and for those of you who are being really polite, because I know I'm perhaps overstaying my welcome, let me show you these two quick videos, and then I really will get out of your hair. I'm sharing my screen now, I thought. Do you see the video windows?
Yes.
It's really weird.
Well,
I don't know. Oh, no, you're seeing this over here. There, my note. Are you seeing this over here, the PowerPoint?
No.
Oh, there it is. That's what I didn't want. But this will work out fine. Let me show you this video here to give you an idea. This is a live video of Albireo A and B. I mean, it's a recording now, but it was live at the time. And it was a mono camera. And you can see that there are two spectra here, and I can never remember which is which. The brighter of the two is Albireo A. So let's look at that video again. I spoke too much. One quick thing the software is doing that I just don't have time to get into tonight. This is Albireo A is, or this is Albireo A. It's a type K star. No, it's a type. Where is it here? Do I say it down here? Well, whichever. Oh, it's I don't know which star it is. I think my notes here are wrong. Notice how all the light intensity is over here in the blue region. This is a hot star.
13,000.
So this is the Planck curve for that star. And now I'm just going to play the video. This is in real time. You were asking about real time. This is using the camera control tools in the software. I'm going to change this region I'm sampling. And now notice this star, which is much cooler, its Planck curve data is piled up in the red end. It's got more light in the cooler end than the hotter end. So that's the kind of thing that you can do. Now, the other thing, and this isn't a product of mine, so I hope you'll forgive me if I show it to you. There is, for those of you who do solar outreach, which is my preference now because I like seeing who I'm talking to, and because you don't trip over wires and I get a full night's sleep. This is unfortunately a $1,300 spectrum tool, a spectrometer, and it's embarrassing quality. This is my iPhone on the curb in front of my house to show a friend who wanted to know how it did. There's a magnesium. I think that's a magnesium triplet. And I'm moving a little bit over. You'll see in a moment. Those things going across are all.
We're not seeing it.
I think the screen share went away.
Yeah, you flipped it back to your camera.
Oh, really? Well, let's try it again. Thank you for saying that.
Try using Alt Tab and well, no, you're sharing your camera. You're gonna have to share your screen again. So
okay, let's do that. I don't know how that's dropping out, but let's do that. I think you'll get a kick out of this. Let's give me a second to see if I can make it happen. We'll pause this video. Thanks for interrupting me. That would have been no fun for anybody. And we're going to share this application, which is that one. Okay, can you see that little video window now?
Yes.
Okay, great. So the deal is with this spectrometer mounted on a tripod, you don't even need guiding. This would be an auxiliary accessory to further engage people in solar outreach. It's got a little gnomon here you use to point, and the sun's so big and bright, you just have to move the thing every 5 or 10 minutes and point it again. This lever here allows you to adjust which piece of the spectrum you're looking at because, oh, now it won't play. So I'm not going to be able to show you this. Here it is over here. So this here, that lever lets you choose which little bracket of the spectrum you want to look at because it's so high resolution you can't see everything in one eyepiece. So you can see it's pointing at the magnesium triplet here. Now watch as I hold my phone up to the eyepiece. And this is really, the colors are pretty, and this is something else. Like I said, there's the magnesium triplet. It's 3 lines. As the name indicates. And let's just, we'll scroll up to 1 or 2 more lines. The colors are gorgeous. And people can adjust that lever themselves. They may not know what they're seeing. That was the hydrogen alpha line. And down here, the last line I show you, this is the sodium doublet. So this is all very cool. And like I said, a great auxiliary, but unfortunately, there's the lever there. You can see me moving the lever. It's not inexpensive. So let me stop sharing my screen, and I promise I won't share my screen again. What else? Anything else? Well, it looks like I'm going to get dinner on time tonight. So you all can see me, and there was one other joke that it doesn't go over as well at the end of a talk, especially when it's introduced that way. But you know, my wife always says to dress for success. It's not like somehow I know she wasn't saying that this was it. I know she wasn't saying it because she not literally, but she begs me not to wear this. But if you look right down in here in that robin egg blue, you can actually see the hydrogen beta line. But the problem is, and I know some of you are going to know what I'm talking about, although maybe pretty much everybody here is natural. If you look down, like deep, down there to the root of the hair, there's like some discoloration. It's gray or something. In my salon, they're not picking up. I can't get into them. And I know that you may have experienced some of this around your home. You have other people living in your homes, and but you can see it's really a mess. It's also too hot to wear. So that's why I like to have people be able to see me, because I have other gags like that too. The other one is is when I talk about averted vision. I use these.
I like it.
Good, thank you. It's nice doing it during the chat at the end because then I get to hear people laugh. Anything else?
No, I'm terribly sorry that we couldn't figure out how to pin your video down so we could do
No
both.
apologies necessary. I don't mean to beat you up. It's just what this tool does. There may be a way to do it. You might think about it.
Well, we can probably send some feedback into the developers here and see if they can make some alteration.
Two other
I'm
things
sure
that I think
it's a useful tool.
Yeah, I think there's two other things that you might ask for from them, or two things I missed, whether you want to ask for them or not. In order to see somebody's name, you've got to hover the mouse over them.
Yeah.
And Zoom shows the name at the bottom, which I find really helpful. And the other thing is Zoom actually highlights the person who's talking, and I'm not sure this does. Does it?
It does. It especially there's a way of setting it up so you can do the full screen for whoever's talking.
Well, I saw that. I don't really like the full screen. I like seeing everybody at once during the chat. And I see it does put up that little circle, that blue circle or dots on the upper left corner. It's a little hard to find when you're scanning 25 or 30 images on the screen. But anyway, this worked fine. And I know some clubs are hesitant for Zoom because of some security issues that were allegedly existing in the past. But
I think our major thing is that we're not a fancy group, so we didn't really feel like throwing out money.
You're right. It's $140. It's and this works fine. I'm just nitpicking. Yeah. Anyway, I hope you'll find other speakers to give talks like these. Have you?
We've gotten a few other speakers that have come in to speak with us, and we're very thankful that you were able to come and speak with us. We know you're familiar with the online format from years back, and you're one of the pioneers in this online speaking to clubs and whatnot. So it's a little different speaking to a group of pixels versus a shot of the entire club. So
you're right. It absolutely is. This is easier for me. I like seeing the little stamps. If I could see everybody at once, like I can. Also on Zoom, you can have a detachable window. I pull to a second screen. Then the problem is I don't want people to know that I'm watching them. When I look over to see if people are laughing, and I'm sure. I mean, I was going to call her out earlier. See, she's doing that. Krista, she's been laughing at me ever since we started this chat. And it's great. But if she knows I'm watching, or any of the rest of you, because Ben's also been laughing a lot, I see. And Chris, when I put this thing on, that was one of the biggest laughs of the night, So I'm all over that, but I don't want you to know I'm watching because then everybody gets a little shy, Understandably, I do too. Anyway, listen, I'd like to thank you again. Keep doing that outreach. Let's hope for a better year in 2021.
Amen.
Pretty easy to get better.
It's at the low bar at this point.
Exactly. The bar, I saw somebody recently say the bar is like a line painted on the ground.
Yeah, anybody that trips over it, I guess if you trip over that bar, it's
who created this logo? Any idea at this point?
It was a gentleman about almost 18, 20 years ago did it.
Really? Is he still around?
He's out in New Mexico right now.
Oh.
Because we had to track him down for something a couple of months ago.
Sure, paperwork or passwords, that kind of stuff. I hear that all the time. In fact, when Yahoo groups, some of you may have been members of Yahoo groups, different groups, astronomy groups, they unceremoniously, just with 30-day warning, shut down all their groups. I think they were freaked about security or porn or legal liability in some way. For whatever reason, it was an awful service anyway, but it was free. So they moved over to another, everybody moved over to another server, another service that's really worked out well, but wasn't free. The point of the story is, I'll get there, I promise. The point is that I was on the administrators forum of that new site, and there were a lot of people posting and saying, we don't have any passwords for the Yahoo site because that was set up 20 years ago by a guy. We don't know where he is. We can't find him. We all have passwords enough to get in and moderate, but not to set the permissions so that all of our exchanges will migrate over to the new site. And people were frantic. So I know how those things work, John, where people move on. But anyway, if you happen to run into them someday, you might tell them that I was ranting and raving about it. I'm looking at it now. It's a really beautiful. I mean, the first moment I looked at it, I went, "Oh, this is like pretty noisy," but it's so beautiful. I'm willing to tolerate the noise. Anyway, good night.
Well,
All right. Thank you so much for coming
Thank
in.
you so
Thank
much.
you.
Bye.
Good talking to you. Awesome. That was great.
Okay, that was a little bit better than the last time he actually came and spoke, since we could all see his slides this time. So I was hesitant about him coming back, but no, I thought that was a brilliant talk, and
Cool, man.
yeah, and it was nice. I could actually see what he was talking about this time. Let's go ahead and
Scott,
kill the.
Scott?
hold on.